2 of paper 1. We've just been through all of this, if it loads up. So we've done our straight lines, we've done our rearranging formulae, which we said was very similar. I'd say these 3 questions are almost identical. They're using the exact same techniques. A little bit of Pythagoras, not very difficult. And then our scaling, again, not actually very difficult apart from diagonal lines. I'd say this, to me, is probably one of the harder sections. It requires a little bit of thinking. So the first thing I would do doing these questions is to revise my rules. Okay, so first rule, angles in a straight line add up to 180. So if I say that this is 50 degrees, then that has to be 130 because the whole thing adds up to 180. So that's the first thing I could fill out. Is there anything on a straight line? So there's a straight line here, and there's a straight line here. So these angles have to add up to 180. So I could do a working and actually say 180 take away 63. So that's going to be 117. And over here I could say 180 take away 121. So it's going to be 59. So angle in there, 59. Other rule I know is that angles that are opposite each other are the same. So if that angle is 100, this angle here is 100. If this angle in here is 80, which it is because of the straight line rule, so this is a straight line here, so that's 80, this would have to be 80 as well. I've just realised that's actually not a great example because size-wise they should go around the other way. But anyway, the point is that angles that are opposite are the same. So opposite here is 117, and opposite here is 121. Opposite of 59 is 59, opposite 63 is 63. So with just 2 rules, I've already worked out a huge amount of what's on the paper. Triangles have to add up to 180. So angles inside a triangle add up to 180. So if this angle in here was 20, and this angle in here was 70, if I'm not going to call it 70. That gives me 90, which would make this angle in here 90 degrees. So angles in a triangle add up to 180. We can't use that just yet because our triangle is here, so we need to know that dimension. Right, the other 2 rules are our F angles and our Z angles. So we've got parallel lines. That angle is the same as that angle, and this angle is the same as this angle. So let's see if we can see any F's or Z's. Well, I could do, there's a little Z in there. So that angle there is the same as that angle up there. I could also have said that there's an F angle. I could say there's an F here, which is to say that that angle is the same as that angle. I could say another F. I could say this. It's like a backward F, isn't it? So this angle here is the same as this angle. So there's lots of different ways you can get up to the top of the next angle. I'm going to go with the Z. I think the Z is quite a nice one. We'll Z on this side. So I'll say 59 is the same as 59. And then it's just the same. 59 is opposite, straight line rule, and opposite. Yeah, so once I know this is 59, the angle opposite is the same. Angles in a straight line add up to 180. And actually just look, this whole set of angles has just been transferred up here. They're all exactly the same as those. And that's what's going to happen here. This whole set of angles is just going to transfer down here. But I'll explain why. So let's do the F angle on this side. So this angle is the same as this angle. So that's 117. Opposite 117, straight line rule, and then opposite again. So see how they're all just transferred down easy. And then the last rule was a triangle at 180. So angles in a triangle add up to 180. So I'm going to have to take away 59 and take away 63 to work out the angle that's left at the end. So you can use your chimney sum. It's good to show you're working. So 180 take away 59 and take away 63. That's going to leave me with 58 degrees in here. Okay, so that angle is 58. And don't forget degrees. For angles you're kind of casually working out, you don't have to put degrees on every single one if you don't want. But for your final answer, make sure that you put your degrees in. Okay, so calculate the size of angle ABC, ABC, and that's that. So you could say, to be absolutely perfect, angle ABC, this means angle is equal to 58 degrees. So there's quite a lot in that. That's the most working and thinking I think we've done in this, the entire section so far. There's been nothing particularly difficult. So I can understand why that's why people do find angles tricky. But you can see there's actually, once you know this angle, this comes quite naturally, and then we basically copy it. Once we know this angle, this comes quite naturally, and then we copy it. So when you break it down into its parts, it's not too bad. I would put a little revision of your rules on the side, just to remind you of what's what. Straight line 180, opposites are the same, triangles 180, and then you've got your F's and your Z's, where this is the same as this, and this is the same as this. And I've just drawn in a little Z and a little F. This is another good rule. Angles inside a circle, triangles inside a circle, this will always be 90 degrees. Because when the base of the triangle is the diameter of the circle, and then these two lines meet the outside, the circumference of the circle, we get 90 degrees. In the same way that if I was to draw a triangle down here, like this, just imagine, I'll redraw that. Just imagine that as a decent drawing. That would also be 90 degrees in there. If I was to draw this, that would also be 90 degrees. It wouldn't be 90 degrees if I was to draw this. There's a line, two lines, and that's not 90 degrees, no, because the base of the triangle is not the diameter of the triangle. So no, that's 90. Angles in a triangle are up to 180, so 180, take away 90, take away 65, is going to leave me 25 degrees. And again, I would show my working for that. I would just say 180, take away 90, take away 25. Sorry, take away 65, leaving 25. The other way to think on that is that if this is 90, and angles in a triangle add up to 180, both these have to add up to 90, because 90 plus 90 is 180. So just save you doing the hassle of always taking off that way. So yeah, you're going to get 25 degrees. Getting to the end of the paper now, just a few more questions. Question 10, calculate the length of the line. This is just a simple Pythagoras question. We cannot work out the length of a diagonal line unless we break it into its horizontal and vertical components. So a little right angle goes in there. So how many boxes are we going along? 1, 2, 3, 4, 5, 6, 7. How many boxes are we going up? 1, 2, 3, 4, 5. This line here is opposite the right angle. I'm going to find that line. So the line opposite the right angle is the hypotenuse. So if I don't know the hypotenuse, I am doing Pythagoras add. So 7 squared plus 5 squared is equal to x squared. So it's a takeaway, Pythagoras takeaway when you do know the longest side, but I don't. So 49 plus 25 is going to give me 74. So 74 is x squared, and then I take the square root of both sides. Square root of 74 is equal to 8.6. I'll just say units. It's units or squares or whatever. So if they just showed you that, it's quite difficult, but the fact they've drawn it out for you does mean it's quite easy. You're just drawing a right angle triangle, counting your boxes and doing Pythagoras. Now we're getting into our trig, because we've got a right angle triangle, but this time with an angle. So the minute you see there's an angle given inside a right angle triangle, you should be thinking trig. Okay, if you see a right angle triangle, it's probably Pythagoras. If you see an angle inside it, it's probably going to be trig. So calculate the length x. And the first thing we want to do is label up our triangle. So if we're using this angle, the side opposite is this one. The side adjacent is this one. Now you could have said this was the adjacent side, couldn't you? But it can't be because that is the hypotenuse, because it's opposite the right angle. So that's me labeled up a triangle. Now I'm going to say, right, what do I know? Well, I know h. I'm trying to find o. So I'm going to use so, ka, or toa. It's going to be so, because I don't know the adjacent, so I can't use that or that. So I'm going to say sine of x is equal to opposite over hypotenuse, so. So that means that sine of 65 is equal to x divided by the hypotenuse of 10. I want to solve for x, so I want to get rid of this 10. How do I get rid of divide by 10? Well, I times both sides by 10. So sine of 65 multiplied by 10 is going to be equal to x. At this point, I can use my calculator. Or in my case, my calculator app, which is why I keep able to unlock my phone. How annoying. 10 times sine of 65, so that's going to be equal to 9 point, and I'll just round this to two decimal places, so 0.06 that's going to be, and our units are centimetres. So 9.06, solved. So label your triangle up, decide if it's sine, cos or tan you're using, substitute in, and then maybe a little bit of rearranging involved. I'm just going to move this whole bit over to here. Okay, the diagram shows a ramp. I love a ramp in these questions. Calculate the size of angle X, and then decide if it's safe. Okay, well first of all is angle X. This is my angle, so this is opposite. This is adjacent. This is my right angle, so that is the hypotenuse. So I know opposite and I know adjacent. I'm going to be using tan, so that's TOA. So tan of X is equal to 830 divided by 7200. If I want to get X on its own this time, I have to say tan of negative 1 is equal to 830 divided by 7200. All that is shift tan on the calculator. A lot of people want to divide by tan. What does that even mean? You can't really divide by tan. This is a function. You put something, it's like a black box. You put something in the box and it spits something out. Okay. If it's on this side, it's tan of X. We want to do the inverse of that. So if to get that to the other side, we're going to say tan to the negative 1, which is just a fancy way of saying the inverse of tan of this. And to do that on your calculator, it's simply just shift of tan. And then we do 830 divide by 7200. So that's an angle of 6 point, and I'll round it to one decimal place, call it 6.6 degrees. So label up your triangle. We found out it was tan. The only bit we had to do that was a bit tricky was get the tan to the other side, which is simply shift tan. That's 6.6. And the very last question says, is the ramp safe? Well, I would say, yes, it's safe, as 6.6 degrees is between 5 and 7 degrees. Simple. So conclude and give a reason. And the very last bit is scattergrams. So we're going to draw a line of best fit, I think, time-wise. Okay, I'll try and do this in one video. No, I'll stop there.